So good morning everyone. We're going to start off with 3 series of lectures by Sushan Konar from NCRA, and this is the first one. So good morning everyone. We're going to start off with 3 series of lectures by Sushan Konar.
Thank you, Priya. Let me begin by thanking Professor Najam Hassan and Professor Priya Hassan for doing this for last 4 years continuously, and we started during the pandemic, and we all know, people who have attended the previous ones, how it has affected our lives, everybody's life, through the pandemic. There won't be any echo, right? No. Okay. How it has affected our life, our lives during the very difficult phase, because we could concentrate on beautiful, abstract, scientific problems where all the difficulties were raging around us. So, great sense of gratitude. Thanks to both of you. So, the name of my topic this time is Death of the Dead Stars. They're already dead, and I'm going to talk about death. So usually this is about neutron stars. Usually what I do is I begin with an introduction to the neutron stars and then go on to define the problem. And in the last few times, we had done it leisurely with some gaps and detailed lectures. So all those lectures are online, and there are quite a few people who have listened to those lectures. And so I decided this time, instead of taking the same route, and also because this is a proper workshop, not a leisurely thing like during the pandemic years, I would skip the detailed introduction. And you may all have received the mail in which I have listed a set of lectures, which are the older lectures. If some of you wish to take up the project on neutron stars, you can go there and listen to those lectures and familiarize yourselves with the basic stuff about neutron stars. So this time I'll skip it mostly, but still, because there are people who are new to these activities, I will give an absolutely bare bones introduction, just so that you understand the problems that I'm going to talk about. So there will be 2 problems that I'll define, but so let us first start with something that comes before the introduction, the resources. Usually people talk about resources the end of everything, but we'll begin with that. So let me share my screen here. You have one. Yes, right. Yeah. Visible, right? Okay. So the purpose of the workshop this time is astronomical data analysis with Python. And what we will do here is we'll use Python to solve certain problems, investigate certain problems in the field of neutron stars. So first, the resources. This is a series of lectures which I gave in 2019. This is an IUCAA repository, 6 lectures, and a detailed introduction on neutron stars. You will get all the links in Priya's email. So you can either listen to this, or there is another set of lectures. This is 4 lectures, which was the first 4 lectures in 2020. And this is hosted by astronomy, and this first set and the second set are more or less similar. The first set may be a little more detailed, not much more. Okay, now what we would do, we are talking about data. So I have listed a few databases that we will access, from where we will take the data for our investigation. The first one is the ATNF pulsar catalog, which is the main repository of the neutron stars. Now today we have seen about 4,000 neutron stars, mostly in our galaxy, only a few in outer galaxies meaning LMC and SMC, not very far. So about, of those 4,000, about 500, roughly 500 are in X-ray binaries. So they emit mainly in X-rays. Those are not in this catalog, but all the other varieties of neutron stars, mainly the radio emitters, all of them are there, and we will go to this site and check things out a little in a bit. Then what we will need for the first problem, what we'll need is a catalog of nulling pulsars, and maybe I can show you the catalogs as I go on, or no, I have to unshare and share again. So we'll do that later. So now the nulling pulsars are a particular type of pulsars, which I will talk about in a while. Now this catalog did not exist, and in 2015 a project student came and he basically trolled the literature and sort of created this catalog. So it is hosted in my homepage. And then we would also talk about RRATs, the rotating radio transients. And these objects, there is a formal public catalog which is called RRATalog, and that is this site. But unfortunately, the site is not very complete. When we wrote a paper in 2022, which was written by people like you from the 2020 batch of the first batch of this series, and so we made this catalog. Only about half of those RRATs are in the public catalog. So we also have this catalog, which is, for the moment, it is not up because there are certain glitches. I will go back to Pune and sort of make it alive again. Just give me a second. I need to change my spectacles. Okay. So these are the sites that we will require for the first problem that I will talk about. And then there are another problem that I would talk about would require the bottom three sites. Also, of course, the ATNF site is always has to be there for any kind of neutron star data work. The globular cluster pulsars, the galactic millisecond pulsars, and the gamma ray pulsars. So these three sites would also be required. These we'll probably talk about tomorrow. Okay. Now, quick introduction to neutron star and associated issues related to neutron stars. There are four. This is also a series. 4 popular articles that I wrote in 2017. These are available on Resonance website, and these are accessible to BSc students. So all of you should be able to understand this at that level. Now, people who would want to get onto neutron stars a little more, there are these excellent books in order of difficulty. Can stars fine piece by Professor G. Srinivasan of Raman Research Institute. He is retired long ago. And this is an excellent book, which again accessible to all BSc students. Then there are various other neutron star books, so you can access them as and when you need it. So this list can be useful. And this is one thing I want to advertise before I begin. This is a 40 lecture introductory astronomy and astrophysics course given by Professor Srinivasan last year, and it's hosted by Astronomical Society of India website. And so this is a complete self-contained astrophysics course. So those of you who would not have any opportunity to take proper astronomy course somewhere, you can go listen at your leisure. And this is a sort of self-contained complete astronomy course. And this course has lectures, and as well as every lecture has supplementary material in the sense of suggested reading, problem sets, etc. I created them. So. Okay, so now get to the neutron stars. Okay. So as I have said, neutron stars are mainly seen as radio pulsars. They are seen in the entire electromagnetic spectrum, from gamma rays to X-rays to optical to radios, but it is in radios they are detected most frequently. Number one, because as you know, if you are slightly interested in astronomy, you would know that only optical and radio wavelengths are visible from, meaning detectable from Earth. For every other wavelength, you have to go to space or at least fly a balloon and do some such thing, right? So all our ground-based observatories are optical observatories and radio observatories, and among them the radio observatories, because the wavelengths are much larger, the sensitivity is very, very high. So therefore we see in radio much better than we see in optical. Can anybody tell me why the sensitivity is much better in radio? The resolution is much better, sensitivity is much better.
Atmospheric transmission.
No, plays a role very, very insignificant. It plays a role in optical.
Interferometry.
What do you mean by interferometry? Correct answer, but
Basically, two telescopes act as one telescope.
and how does that help us? How can two telescopes act as one telescope?
Each telescope captures one Fourier component of the signal.
Each telescope?
So each dish captures one Fourier component of the incoming signal, and then it
Is that possible? Does the telescope know which Fourier component it should pick up?
It is done in the back-end electronics.
That one Fourier component would come to one telescope?
No, so it is. I'm not very sure, but then they are like for the example of GMRT, we have 4, 3, 5 possible combinations of the antennas.
Right.
So we just each pair takes one. I'm not again very sure, but each pair takes on one component of.
Okay, so you are there, but not really. Anybody else knows? That is going into much more detail. So simpler answer, anybody knows? It is due to aperture synthesis. Simpler answer is
they have longer wavelengths so that they penetrate, they don't distract in medium.
no. The simplest answer is because they are much larger wavelengths. What people were saying is correct. Everybody what you were saying is correct. Is if it is a very large wavelength, then you see if the telescope takes the signal now and takes the signal 5 minutes later, then it is not seeing the same object, right? Because this object in 5 minutes has changed to something else. So all the telescopic components have to see it at the same time. call it coherence, right? So if it is large wavelength, so it would remain coherent over a large length, bigger length. Okay, so we can have, first of all, we can have bigger dishes. Optical in optical astronomy, keeping coherence with very bigger dishes is very difficult. No, the focal plane has to be really accurate. In radio, you can forget about that. The wavelength is very large, and so therefore you can have large antenna, large dish, and if you have large dish, you can collect more signal. It's like, you know, long aperture photography. If any of you do, everybody does cell phone photography these days. If anybody does serious photography, would know that, you know, if it is faint light, you have to collect more light. So you have to keep your camera aperture open for a longer time. So you do it in a different way. You have a bigger dish, you collect more photons. So anyway, that is digression. So therefore, we mostly see them as radio pulsars. Detection in other wave bands has happened, keeps happening, but this is the easiest. So now neutron stars are very special kind of objects in the sense that, as you know from the name, neutron stars are mostly made up of neutrons. So it's 90% neutrons, 10% protons, and same amount of electrons. I mean, same as the protons to keep it charge neutral. That's why they are called neutron stars. Now, the concept of neutron stars were theorized by people like Lev Landau and Chandrasekhar even before neutrons were discovered in laboratory. So even before this particle neutron was discovered, Landau had an idea that they may form an object which will be of a very small size, and it would have certain such properties. And if you want to know this very interesting history as how Landau came to that, those of you can please go and look at this particular paper. It's not a paper, it's basically historical account of how this idea came about. And this is happening in 1930s. And the actual discovery of neutron star is happening in 1967. So more than 30 years before it was discovered, people thought about it, considered the idea, the theoretical idea. And this is the first detection of a pulsar, a neutron star. So there was something going around in the sky with a period of 1.33 seconds. And it was discovered that it cannot be anything terrestrial, skipping sidereal time. And then later on, people realized that this is a radio pulsar. People who are not familiar, this particular graph may not mean much, but if you can see that there is slight signal here, and there, these are the pulses. You have to take out a lot of noise in order to see the pulsar, but this is just a history. Okay, so what are neutron stars? These are the end states of stars. Now, you all of you are interested in astronomy, and you know that there are stars, there are galaxies, there are galaxy clusters and various things. But astrophysics and astronomy starts with stars, right? Actually, it starts with the planets and stars. So now, does anybody know what is the mass of our galaxy? Rough idea? Numbers? How many stars in the galaxy?
400 billion.
Around 10 to the power 11 stars, and therefore mass is about roughly 10 to the power 11.
45.
Solar mass, we would say solar mass. So roughly 10 to the power 11, 12 solar mass. So, and what is that telling you? that on the average, the mass of the stars is about a solar mass. Maybe a little more, but about a solar mass. Okay, so the most interesting fact that you should remember about stars is that the mass of the stars falls within a very narrow range. 80 times Jupiter mass to about 100 times the mass of the sun. That range, in the universe, there are so vast amount of things are there, but the stellar mass falls within this small range. And what we call, so less than 80 Jupiter mass is not stars. So what we call our big objects are failed stars, mass less than 80 Jupiter, which are not asteroids or small planets or something like that. So something like Jupiter is called a giant planet. Jupiter is very different from Earth. It's a gas giant. So it's a very different kind of thing. Had the mass been a little more, it would have been a star, right? It's very, very different from Earth, right? Because Earth is a solid body, Jupiter is not. So these are different kind of objects. And then there are brown dwarfs between 13 Jupiter mass to about 80 Jupiter mass. They start the nuclear fusion, sort of proceed towards becoming a star, but then can't finish it. It sort of stops midway because their mass is not, they're not heavy enough for the temperature to go high up and for transformation of hydrogen into helium. So now, then these are the stars. At the end, so when do I say a star is alive? Give me name of a living star. Sun. Okay, so a star is alive when it is running fusion engines inside its core. So hydrogen is becoming helium, helium to carbon, and so on and so forth. Okay, so when that process stops, many stars like our sun, they would shed the outer envelope and would become a white dwarf. More massive stars would undergo a huge explosion called supernova, and they would either become neutron stars, but if they start with being very massive, they would become black holes. So neutron star is already a dead star, right? It's finished its activity, now it's a dead star. So we are talking about the death of these dead stars. Why? Because after all, neutron stars, we are seeing them, right? As neutron stars, we see the radio pulsars, we see whatever. So there comes a time when we cannot see a neutron star. It's not emitting. I mean, maybe it's emitting, but it's so faint that we cannot see it anymore. And that is the phase the death.
It reached such a tremendous speed that the earth curved away before
Somebody is saying,
it reached the ground.
okay, so that is the process, and that is the phenomenon that we would investigate here. Okay, all right. So far, no issues, right? Now, so a quickly saying. So, as you know, white dwarfs, if the mass of the star is less than Chandrasekhar mass, which is 1.44 times the solar mass, that goes from a main sequence. Main sequence is when hydrogen is becoming helium, to a giant red giant phase, then goes to a planetary nebula and leaves a white dwarf. If it starts with a mass of 8 to 25 solar mass, this is the beginning mass, right? Goes to a main sequence, blue giant phase, goes supernova, leaves behind a neutron star which could be as massive as 3 solar mass. We recently have something which is about 2.72, I think, solar mass. And if the mass of the beginning star is even larger, then it will, after the supernova, it will leave behind a black hole. Now, black hole is something we would not talk. Okay. So they are seen as radio pulsars. How? So what is the source of emission? Normal star, there is this nuclear engine running inside it. A lot of heat is being produced, and that is coming out as radiation throughout of all over the electromagnetic spectrum. Now, neutron stars do not have that engine running. Okay, it's all done. It's a solid. It's a piece of solid. So how is it radiating then? It is radiating because it has angular momentum. It's rotating fast. And it also has a very strong magnetic field. So I'm sure most of you have studied in your electromagnetic course that if you have a magnet which is rotating around an axis, it would radiate. And exactly same thing is happening here. Okay. So now the process of pulsar radiation is very, very complex, and people are still not confident about the correct theory. So you would not go into the details of pulsar emission mechanism. We would simply understand it's something like a huge bar magnet. It's going around its rotational axis, creating a very large electric field, because bar magnet going around some axis, so it creates a very strong electric field. This electric field creates charged particles. How does it create charged particles? Because of this very strong electric field, it pulls out electrons from the surface of the neutron star, and it can also give rise to electron-positron pair creation. Because of the very strength of the field, it can give rise to electron-positron pair creation. Okay, so this is how charged particles are created in the region we call the magnetosphere of the neutron star. What is the magnetosphere of the neutron star? It's the region right outside the neutron star. Now look at this little carefully. Here is the neutron star. This figure is not up to scale. Okay, please remember that. It's just schematics. So here is the neutron star, which is about 10 km in radius. It has a strong magnetic field, and this is the rotation axis. Now you will see that this is something called a light cylinder. This line you see here, it's called a light cylinder. Now the neutron star is rotating. Therefore, at a distance from its center, the radial velocity is omega r, where omega is angular speed. So there would be one distance, let us call it LC, immediately know why, where omega multiplied by LC becomes equal to C. Right? Now, nothing can go faster than C. So therefore, magnetic fields which are contained within this light cylinder would rotate along with the along with the neutron star, but the magnetic fields which are not contained within this light cylinder, they are open field lines. They would trail behind, because in order to co-rotate with the neutron stars, these field lines would have to go at a speed faster than C. Now you would say, field lines, it's an abstract concept. How does it matter if it goes faster than C? Because the charged particles, the simpler answer, there are more complex answer. The simplest answer is charged particles in strong magnetic fields would be tied to the field lines. They would move, but along the field lines. So if you had electrons moving along the magnetic field lines, and if the magnetic field line was co-rotating with the neutron star, those charged particles would have to go faster than C. And that cannot happen, right? We all agree. Physical particles would not go above sea. So therefore, this is a very special region. This region is very, very special, where the magnetic field is co-rotating with the neutron star. All the charged particles moving along the field lines are co-rotating with the neutron star, and a lot of interesting things are happening here. So that's the light cylinder region, and that is what we call magnetosphere. Okay. So here, so there are the processes of radiation generation, synchrotron radiation, Compton scattering. Radio radiation mainly comes from this Compton scattering, curvature radiation, etc., which I would not go in the details of. Anybody who is interested can go look up. Not Jackson, not Griffiths, Jackson. Griffiths doesn't have all this in great detail. Anyway, so what we have measured. So why does it get the name of pulsar? You see, if you consider this picture, there is this cone that is created by this geometry, from where particles can come out. These particles are moving along the magnetic field. So the radiation can come out like a beam, like a lighthouse beam. I do not know how many of you have seen a lighthouse beam, or at least have seen pictures, movies. So because it is rotating, we get this beam. It points to us once every period. It's going around, so this beam is coming towards only once, right? And then it goes in some direction and then comes back. So what we see here, we don't see something rotating. We see a pulse coming, then another coming, then another coming, and this happens in a periodic sense. Because every period, let us say the period of a pulsar is 1 second. So every second we get a pulse. After every second we get a pulse. So that is why these are called pulsars. And because we are seeing them in radio pulsar. So that is the meaning of the name radio pulsar. And typically we have observed the spin period from about a millisecond. The fastest observed is 1.3, I think. You people know better, right? Now, when I prepared the slide, sorry, this slide was prepared a while ago, and I wrote 10 to the power 1.5, which means about 30 seconds. But I'll show you a picture later. Now we have radio pulsar observed with a period of 1,000 seconds. So it now spans a range from 10 to the -3 to 10 to the +3. Okay. And so therefore, plethora of physics happens because 6 orders of magnitude difference in rotation. Surface magnetic field. Again, this slide is slightly old. I wrote 10 to the power 8 to 10 to the power 15. Now we have 10 to the power in Gauss. People who are familiar with Tesla, please convert in your mind. 1 Tesla is 10 to the power 4 Gauss. So it goes from 10 to the power 8, not 10 to the power 8. It goes from close to 10 to the power 7 to 10 to the power 16 Gauss. Now 10 to the power 16, I must admit that it's slightly controversial yet. Last year I wrote a paper saying that some object must have 10 to the power 16 Gauss, otherwise its physics cannot be explained. I was slightly sort of apologetic about it. The paper is published and everything, but then Russian group, whose calculation I always trust, Russians are very good at difficult mathematics, so they also think that 10 to the power 16 Gauss seems to be the right number, so I'm happy. Anyway, so now if we believe in this model of the pulsar, this magnetic field rotating and therefore giving rise to the radiation, then this radiation has to come at the expense of some energy. Radiation means energy, and if you are throwing out energy, this energy has to come from somewhere. From where can the energy come from? Rotation. It comes from rotation. So therefore, this object has to slow down. So if it is slowing down, then dE dt, the change in the rotational energy, can be calculated simply, right? I omega omega dot, simple calculation, where I is the moment of inertia of this object. And if we believe in this dipolar model of radiation, then if you go back to the emission from a magnetic dipole, then you would see that there would be a constant here, of course, omega to the power 4 multiplied by b square. So I omega omega dot is proportional to omega to the power 4 b square. You see something interesting here? I can measure omega, which is the rotation rate. I can measure the omega dot because I can measure how it is slowing down, right? From a continuous measurement of omega, I can also measure omega dot. I cannot measure b. But if I can measure omega and omega dot, then from my theoretical model, I put some reasonable number from the moment of inertia, I can get an estimate for the magnetic field. And that's the holy grail of neutron star astrophysics. Okay, handle on the magnetic field. And that's what we do. So now that we have sort of set our instruments, sort of, so to speak, all our tools are here. Now let's go into investigating what is happening with what are the peculiar things happening with this radio pulsar. Everything is not this nice. One of the things that happens with many radio pulsars is a phenomenon called nulling. Now, this is a schematic diagram for a radio pulsar. You got a train of periodic pulses. Now there is something called nulling pulsars. Nobody knows why. Some of the pulses are missing. Just not there. Then again, you get regular pulses. Again, some of the pulses are missing. Now there are...
Is it the same as glitches?
No, glitch is another kind of thing. So then there are... yes?
And this nulling is not symmetric. Like it's not happening. Once it's happening and then it's normal and then again happening. It's not regular.
Oh, no, it's not regular. Life would have been beautiful had it been regular. No. Some people have seen some quasi-periodicity in a few objects, but that's not the typical behavior. Okay. So now there are objects which show extreme nulling. Extreme nulling. And there is a famous case of a PhD student who was working on one of these extreme nulling object. He had to redefine his thesis because this fellow went in nulling and did not emit again before his thesis was finished. He had to submit. So astronomy research has all these peculiar side stories. Anyway, now and then there are R-rats. Now, R-rats are even more extreme cases of extreme nulling, in the sense that you would see a pulse only. There is no guarantee when you would see the next pulse. You may or may not see the next pulse, and you may see the next pulse some arbitrary random time and then another at another random time, and you would understand the difficulty of doing any piece of physics with such an object, because if you see this object in some region of the sky, the telescope is not going to point to that direction all the time. The telescope would do various other things, right? Because in any observatory, you write a proposal to see a piece of sky or a particular object or something, and then the telescope would be given to, sometime it would be given to you, then it would be given to another investigator who has his or her own things to see, right? So telescope is not going to sit there. So if an object is this sporadic, this irregular, it becomes extremely difficult to investigate that.
How do you know it is a neutron star?
There are
Or a
various
pulsar?
various other things will happen to it. Yeah, I will come to that. So there'd be various indirect methods. I will come to that. Okay. So now, one of the arguments in nulling pulsar research is nulling pulsars were first discovered in 70s, I think in 72. But the R-ret phenomenon is very, very new. It's 2009. Okay. So what people thought is that R-rats are nothing but an extreme form of nulling, and there is really nothing to say that they are not. They should be some extreme form of nulling. Now, one of the work that we did in with the 2020 batch is that, as I said, that we created this nulling pulsar catalog. We did not have a catalog, so we created that catalog. Then we took the existing R-rat catalog and we again did some literature trawling, created our own updated R-rat catalog, and now we had this set of objects. There are these nulling pulsars and there are R-rat objects. What you can do with such objects is, you may not have an handle on the emission process, why the pulses are disappearing. What you can do is, you can look at other properties of these objects and you can compare the populations. And that's what we did. So,
One question.
Yeah.
In RS,
Huh.
are the pulses always of the same power, same strength? The pulses.
the pulse strength, yeah, similar. Similar. I mean, yeah, similar. Yeah. The interesting thing about R-rats is the pulse property, all kinds of properties. I mean, as you have said, the power, pulse power, and the nature, the profile, etc., is very similar to regular pulsar as well as nulling pulsars. They are similar, but so as you can see, regular nulling pulsars, which we do not call extreme nullers or R-rats, also have very different kind of behavior. You see, these black things are the pulses. These are stacked in time. So this axis, the y-axis, is in time. So you see pulses, and then there is gap, then there is gap, then there is gap. Okay? And there is a question that whether it's regular. You see, it's sort of semi-periodic here. Here you see the gaps are much bigger. The pulse phases are much shorter. The gaps are much bigger. In the next one, the gaps are shorter. The pulse phases are much bigger. This one is an extreme case. Only one in this entire observing period, only one little bit of pulse. It was sitting there doing nothing, and similar stuff. So they, even within the nulling pulsar set, very different behavior. So why are we saying that they are similar? Because what I said in answer to Rita's question is that the pulse profiles, the nature of the pulse, the subpulses, the structure of the subpulses, the energy in the pulses, they are very similar. So they are considered to be of the same group. Okay, now before I go into the alright issue, is that first of all we have to try to understand what is happening with the nulling pulsars. Now people give various explanations for why the pulses disappeared. Okay. One of the very early explanations at the time when there were not many nulling pulsars, I think 6 or 7 nulling pulsars were observed. One of the very, sort of one of the radio astronomers with a very great knack for knowing what really is happening, Joanna Rankin, she said these must be associated with the pulsars getting old. They are getting older, which means they have slowed down much more, and the process that creates charged particles in the magnetosphere of the neutron star, that process is becoming inefficient. It's sputtering. If you suppose you have opened a tap and the water is flowing, when you are stopping it, even when the cork is fully closed, there'll be some drops coming out, and then it properly ends the flow. Okay, so it's a process like that. So it's the mechanism had started to sputter. It's happening sometimes.
But then the periods would have been reduced. Oh, sorry, I'm getting,
Yeah. So
is it noticed?
I'm coming to this. This is the picture. Okay, so this is a picture, and similar pictures you will see many more times. This is the y-axis is log in magnetic field, and x-axis is log in spin period, and all the small dots, they are all radio pulsars. There are 3,500 objects here, which you probably would not really have a feel for, but that many objects are there. And what you see here, these circles are the nulling pulsars. Okay, and you see 2 lines. What are these lines? I have marked them as DL1 and DL2. Okay. So these are the death lines, because you see there are no pulsars in this region. Nothing here. And this is the region we call the pulsar graveyard. What is happening is a radio pulsar, when it slows down, it would start moving towards the right. Okay, so and around this point, what happens is the combination of the spin period and the magnetic field becomes such that the emission process do not work anymore. So then there is no emission happening from the neutron star. The neutron star is there, but we do not see it as a pulsar, and therefore we call it a dead pulsar. Okay? So that is the death of this dead star. So it goes beyond the death line. Okay. Now, why have I drawn 2 death lines? There are actually many death lines, depending on the assumptions that go into the physics of emission mechanism. As I have said, lots and lots of uncertainty in that emission mechanism, in our understanding of the emission mechanism process. So people make various assumptions, and depending on the assumptions, they draw their death lines. The many death lines, some of them are in a completely crazy direction. I have no idea why do they make death lines which do not fit the data at all, but they make such death lines. These 2 are sort of the most, what should I say, the most accepted ones in the community. As you can see that these 2 seem to kind of contain the data very nicely. We do not have anything on this side. So, and you'll see that it's not yet clear. You see that these nulling pulsars are somewhat bounded by this line. Now, we had a conjecture saying that the only thing that would prove Joanna Rankin's assertion completely is if we have a crowding of nulling pulsars around this region, so that, too many nulling pulsars near the death line, that would prove Joanna's assertion that these are getting older and therefore they are nulling. And we submitted a GMRT proposal, and the data seem to be showing, is going into our favor. So we are writing that paper up.
But there are still some pulses between the two lanes.
Yeah,
Normal.
yeah, normal pulses. Because you see, the parameters that go into these assumptions, they have huge range. So these lines are not, not very. They should not be taken very seriously. They're just kind of limits. So, as I have said, then there are whole bunch of death lines. You see these two death lines. Where are these? They are above the data, but people still consider these as death lines. So, and nobody takes them seriously, obviously. So these are the death lines, and do I have the? Okay, so these blue stars are the extreme nulling objects. But from this picture, at least, we do not see anything particularly special about them. So they are some. Okay. But it is clear that the nulling pulsars are sort of bound by this death line. And what it tells us, apart from anything else, see, all these lines have, as I have been saying, they have different assumptions about the nature of the field lines and the nature of the emission and so on and so forth. Now, if the nulling pulsars are roughly bound by this line, it means that most of these objects have twisted kind of magnetic field, not simple, nice dipole, but twisted kind of magnetic field. And evidence of that has been seen in a few objects. So that is a possibility that the pulsars which are showing nulling are old pulsars, but also have a particular type of magnetic field. So that's one of the things. So when is the thing?
10 minutes, 5 minutes.
Okay. Yeah.
What the reason for twisting magnetic field? How did it create?
One of the very difficult questions, which I do not know the answer to. See, the generation.
Cracks in the grass.
No, the thing is, the generation of magnetic field itself is a very sort of still debated question 60 years after the neutron stars have been detected. So there are many theories, but why a particular system has a particular type of magnetic field is not clearly understood. So it has to do with the dynamo processes that run at the time of the formation of the neutron star. When the neutron star is formed right after the supernova, it's a fluid. And there are these currents are moving around, and dynamo processes are going on. And then this neutron star cools down very fast, and that field gets frozen in. Okay, so instabilities and various uncertainties there would give rise to different kind of field structure.
But has it been correlated with age?
Yeah, we did some calculation to show that if there are higher multipoles in the magnetic field, they would dissipate out quickly. The dipolar component would be long-lived. But if you have toroidal fields, now the current understanding is there has to be toroidal fields underneath the crustal region. And if the toroidal field interacts with the field, then with time, and then you throw in glitch and cross cracking and everything, one doesn't know how it would change the configuration.
Yeah, with the age of the pulsar.
With the age of the pulsar, yeah, that's what. With time, things would change.
So are these whatever extreme nulls, are they old?
They are not particularly old, not older than the average. Some old, some not. So no, nothing special about them. Yeah. Hmm.
That there are no running pulsars are detected yet, or it's not actually
No, they are not detected yet. See, it's not. Okay. Yeah, I'll answer her and then.
You'll see that.
Yeah. So the thing is, as of now, we see that the nulling pulsars seem to be sort of limited by this one. Tomorrow, if 5 nulling pulsars are detected below that, then we have to rethink. This is how astrophysics research goes. Okay. There seems to be a question, you said?
Have some next question.
Should I read it out?
Yeah.
It's there, na, here in the chat. If we obtain magnetic field from the change in period, then how do we know about
Okay.
multiples of-
Yeah, very, very good question. If we know about magnetic fields from the dipolar, dipole field radiation, yes, of course. If we make that assumption, we are not allowing any kind of field structure apart from the dipole, right? But real life is not like that. When you look at the profile, you know that this particular profile, to explain certain profiles, you have to invoke higher orders of multipoles, sometimes much more complex geometry. So that comes from the looking at the details of the pulsar emission profiles. This assumption only gives you a handle on the sort of kind of overall field strength in the dipole component. It does not tell you much more than that. Yes. Very good question.
There are 2 more questions here on YouTube.
Yeah.
Can you explain how we found exoplanets while observing these pulsars? I mean, did we use radial velocity method? The pulsar?
Yes. The first set of exoplanets that were detected, the first ever detection of exoplanets, were pulsar planets. I mean, of course, they won't be habitable or any such thing. Neutron star radiation would kill any living species, but 3 exoplanets circling.
Before Michel Mayor. Much before Michel Mayor.
Yeah.
5 years, I
much
think.
before, yeah.
5 years.
92.
Yeah,
92.
okay.
Yes.
There's another one. How do we know those rats are pulsars at all?
I'll come to that.
Yeah.
The later part. No. If you
Can the nulling be due to wobble?
if you are talking about precision, I'm assuming by wobble you mean precision. No, that would again be. It would not be nulling, but if it's because of precision, that would again be a periodic phenomenon, not irregular thing like a nulling.
Yeah.
No, maybe they mean that this pulse just wobble and skips. Like some
No, that cannot happen. No, that
Avik.
cannot happen. Yeah.
As you say that after deadline, the radiation stops. But what happens to the neutron star? Is it still there?
It's still there.
And is there any recycling? So every neutron star.
That tomorrow. That is for tomorrow. Recycling is for tomorrow.
Okay.
Yes.
What are the subpulses that will build?
Subpulses. You see a pulse, but there might be there might be a smaller pulse next to it. I mean, what I have shown here as pulses, they're very nice and clean, and one pulse and nothing, and then one plug. Real life is not like that.
So like there can be superposition of two pulses.
What do you mean by superposition?
Like one pulse can be superimposed on the other.
No, how would it be superimposed? See, it's a beam of radiation that you are getting. So sometimes you're getting a pulse is a strong radiation. So there might be a little bit of radiation next to it. Maybe in between, if the alignment is such that even in between you get a little bit of radiation, that can happen.
So when we are detecting this kind of hard pulse and then there is a small pulse now, do we neglect the small pulse?
No, we don't.
are
We
very
don't.
considerate.
Important physics there.
Yeah.
You don't throw out data. Yes.
Are the reason for this specific being extremely and the other same? If they are same, then are the
That is the question. Oh, sorry. I'm sorry. Sorry.
if they are same, then RF go closer to rotation.
We'll come to that in the next class.
We have 2 more lectures.
Huh?
Yeah,
So it's equal.
yeah.
Maybe
Thanks a lot.
we can. Like if you, it's no longer equal. No, it's equal.
It's echoing, but this, I actually was trying to do something. Anyway, we are winding up. No,
I will
Ajay.
log out now.
Yeah, you can log. Yeah, so thanks, Sushan, and we have 2 more talks. So Sushan will be with us again after lunch, and now we have 2 rounds of Akshay.